I am very thankful to both of you to give me the chance to talk about the power of mathematics. Mathematics is really a discipline of possibilities. We create tools that will come to answer questions that we have yet to imagine. And there is no better exponent of that our keynote speaker, Ingrid Desbauchies. She has made incredible contributions to fundamental mathematics, but many of you know her from other sides of life. And so I will, many of you have heard about wavelets, about the power of wavelets, about everything that they do to encode in small pieces, lots of data. But I was recently rereading some of the letters that Ingrid wrote to Yves Meyer at the time in the early 80s when she was working on what became the Desbauchies wavelets and many of the other tools that are used on a daily basis. And at the time, she said, "Dear Yves, I have been working on creating these bases for orthonormal bases, orthogonal bases for a Hilbert space. And they're coming, I think you will like to look at them." And if she had sent any of you this letter here, you would have thought, what's she talking about? Well, she's talking about the technology that years later came to revolutionize many of the things that we do now. So that's the power of mathematics. Ingrid has received many honors and awards. She is a Guggenheim Fellow. She is a MacArthur Fellow. She also received honorary degree from Harvard alongside Angela Merkel, the German Chancellor. She's a member of the National Academy of Sciences, the National Academy of Engineering, and the American Academy of Arts and Sciences. And I think one of the things that distinguishes her work is that she has been interested not only in mathematics and its applications, but in its relations to many other things. For example, art. So she was involved in the restoration of the Ghent altarpiece. This is a 15th century piece. You're not going to see it here, unfortunately. You'll see other pictures of art in a minute. And so she worked with artists to restore it, and she actually gave a talk. So just to give you an idea of the breadth of the places where she speaks, at Burning Man, at one of the midnight talks at Burning Man in 2018. Now, what you see is one of the projects on the screen is one of the projects that's very dear to her heart. You are seeing a picture of Mathemalchemy. This is a project that is a collaboration between artists and mathematicians. Came out about, and she will have a chance to explain to you a little bit about it. It came out of a collaboration with a fiber artist from Quebec, last name Herman. And so without any further ado, I would like to welcome Ingrid Desbauchies to the stage for the day that will bring us into the future. Thank you.
So thank you, Tatiana. Thank you very much. And yes? Oh, okay, thank you. So what Tatiana showed you was Mathemalchemy, which is a mixed media art installation that is a traveling exhibit. It's now setting at its 6th venue, and which is, it celebrates the creativity, the beauty, the whimsy, the power and the joy in mathematics. And it does that, it depicts a wonderland, a magical wonderland with critters that live in this world filled with mathematical objects and customs. And we aimed it to be appealing to elementary school kids all the way to professional mathematicians. And so there is a ton of stuff in it. I'm not going to, it was created by these 24 people in a collaborative design and then fabrication, all during the pandemic. So we sent things back and forth a lot on the US Post Service. And it started its exhibition life at the National Academy, at the Gallery of National Academy of Sciences in DC. But right now, many of you are based or will have some time in New York. It's right now in New York, in Manhattan, at the National Museum of Mathematics on the corner of 5th Avenue and 26th Street, and I recommend that you go and look at it. You will get even more out of it if you also explore the website while you're there or beforehand. But that's not what I was here to talk about. I mean, I'm here to give a keynote to today's day, and to be honest, I'm not going to tell you a foretaste of quantum computing or any of the other fantastic topics. In quantum computing, my closest link to that is that I started my career in rigorous result in quantum mechanics, and I'm married to the person who's the C in the foundational CSS paper in quantum error computing. So, so that's not error correction. So that's not. But what I do want to, what I decided to do is, by looking back on this interdisciplinary career I had, where mathematics plays this very fundamental role, is give you a few of my prejudices about mathematics and why it's so important and why it's really everywhere. First, one of my hobby horses, mathematics departments typically have subfields in them. And I'd list a few. I mean, you can name many more. So number theory, topology, and so on, and applied mathematics. I never agreed with this, because it's not true that applied mathematics is there to get another one of this list. Instead, every one of these has applications. And cryptography, topological data analysis, and so on. In every one of these applied fields, the person doing the applications have much more in common with the theoreticians in the field than they have with people in applied fields that use other kinds of mathematics. So all kinds of mathematics, no matter how pure and so on, has the potential, because it's such a powerful thing. As Tatjana said, we build tools in mathematics where not necessarily knowing where they're going to be used. And the beauty is that sometimes these concepts that we build, that we study, that we name, so that we can encapsulate them mentally and then use them elsewhere and reason with them and so on, turn up to be useful elsewhere than where they were first designed for. Sure, so that's the uncanny effectiveness of mathematics, as it's sometimes called. But that's not... when people say the unreasonable effectiveness of mathematics, I never agree with that. I say, as compared to what? We have nothing else. Mathematics is the name we give to that tool that we build to think about these concepts and these constructs. So mathematics can be applied almost anywhere. And all mathematics can have applications in the most unexpected directions. The inspiration for building new mathematics can also come from almost anywhere. And that's why in my life, actually, I have worked in a number of different areas. But they always, I mean, even though they're unrelated, I love talking to people of different backgrounds. And I love learning from them. And that's why I'm so excited to be here, because this is going to be a feast for this appetite for learning and that I always have had. And then I like, because, well, I like to think, so as we all do. It's a very human trait. I like to distill from what I hear things about which I can maybe think profitably and usefully, and distill mathematical questions. And then those mathematical questions, I say, well, if they've told me about something, if I could do this, would this be useful to you? And sometimes it's completely off the mark, and well, so be it. But sometimes they say, oh yeah, that would be useful, especially if you could, and so on. And then when I'm lucky, with collaborators, I find something. And when I'm really lucky, it feeds back to the application. So that's what I really like. And I'm really thrilled today to hear about the things that have been done and that will be done and that are being in construction. So I'm not going to talk to you about all of those. The one field on which I'm very much still working is the very last one, in which we're building tools to actually understand collections that have an organization to them, and we want to understand that collective organization. But each of the samples, each of the data, is something with a lot of structure. So if you imagine all these bones and teeth that we look at with biological morphologists, so we look at, for instance, the second molar of different primates. Each one of them has a lot of structure, but they're organized in something that has parameters that we would like to understand, because we want them to link that to see how it reflects everything we know about the phylogenetic trees that come from genomics, and see how evolution shapes these morphology. And so we have samples, each of which is a surface. And for mathematicians among us, you can model that as a fiber bundle. You have a manifold, and each thing has a lot of... Now, there's a lot of data analysis where each one of the points on this collection that you want to interpret has structure. So we believe that the tools we're building there will have applications elsewhere. That's all I'm going to say about it, but I'm happy to discuss about it during the... Okay, so, but to give an example of where... Actually, this is an illustration of a different point. I once was in the department where I was working. We had a distinguished visiting committee that came to evaluate the department, as they do. And Eugenio Calabi was a member of that. He said, Ingrid, do you know the difference between applied and pure mathematics? I said, well, I think I do, but I'd love to hear what you would say. And he says, well, pure mathematicians, when they're stuck, they say, let me define the problem a bit more narrowly, and maybe then I can... He says, applied mathematicians, when they're stuck, they say, time to learn more mathematics. And that's exactly true. I mean, when you work on applications, the problem and the nature of the problem governs partly what mathematics you bring to bear. And so on different fields that I've worked on, I've had to bring to bear completely different. I came from functional analysis and then I learned more harmonic analysis. But in working with people trying to understand the effectivity of independent component analysis for fMRI, which at first sight, when you start thinking about it, there's nothing independent there, but it turns out these tools are also very good at finding sparse expansions, and that's the important thing. Again, that's all I'm going to say about that, but I had to learn much more about probability and statistics. And then in the morphology, I'm now learning differential geometry again, which the last time I had a course on that was not quite half a century ago, but almost. And the field has changed a lot in that time. Okay, so let me take one of the examples and things I learned. And I also want to tell you how in mathematics and applications of mathematics, different application fields can bring together and bring different ideas, which then together build something that's bigger than each of the parts. So I had this happen to me when I worked on wavelets. Wavelets help decompose information into different scales. Tatjana mentioned them already. So, okay, let me race you through a wavelet impressionistic explanation. Digital image consists of pixels. Okay, so here, let's look at black and white because color is really treated in a different way, and it's amazing how you can trick our color vision. It's actually anybody of you who has an artistic inclination and has used color in that knows how when you have one color and you put another color next to it, your impression of the first color can completely change. That's our color vision. And of course, people exploit that. So let's look at just the luminosity, so black and white. So in an 8-bit grayscale image, you use 8 bits, 0 to 255 in numbers for going from all black to all white. And then so you have 254 intermediate levels of gray. I used to say other people only have 50 shades of gray, but so once you have numbers, you can of course representing these shades of gray, you can use that to compute with them. You can average, you can subtract, you can compare, and that's what you do in digital image processing. So let me, without going through those operations, explain why that is useful. So this is an example from some work that I did with the Van Gogh Museum. These are grayscale images of a sketch by Van Gogh of two clogs very early in his career. And the top is the high resolution, and the bottom is a slight blurring of it. Slight blurring means that you've taken local averages. You've replaced each pixel by an average, a weighted average of the neighbors and the center. And you can then take the difference of those numbers. And actually, I'm showing it here on the right. It's actually emphasized because you wouldn't see much otherwise. And you see that where do you see something is big? I'm really showing big here in black, so I'm reversing. Large numbers here are black and others are. You see that where there were edges. Because where there's a transition between light and dark is where, when you start averaging, you make a big difference. And so elsewhere, like for instance in the background, in the top left, there isn't much happening, so you don't see much. And now let's do this several times, but I'm running out of real estate, so I'm going to show it to you only on a little piece of the whole image, this little piece. And I'm averaging, I'm smoothing that, and again, and again. And every time, of course, you see from the first to the very last, I've lost quite a bit of detail. So I can actually look at what detail I lose every time by taking differences. And here, the color is false color. It's to distinguish positive and negative. Because once I start taking these differences between numbers between 0 and 255, I can get negative outcomes. And again, and again. So if I look at these three differences, who together with the very coarse average would enable me to reconstruct the original, you see that there's some features that they have in common. So, for instance, this edge of the clog is everywhere. And that's because a sharp edge is something that gets smoothed more and more. And every time you lose information, so that's why every time in a difference you find it back again. But there are other places, like for instance here, where if I enlarge that, you see that there wasn't much, there was a little bit, and then it becomes stronger in the next difference, and it fades away again. So this is information that lives at some intermediate difference scale, not at the very finest, not at the very coarsest. So you can actually, and we use this in order to make little summaries of paintings, of the style of a painting, by looking at this collection of at every place, at what levels does information exist, at what orientations, and that gives us little feature vectors. So a painting could be represented by a whole lot of feature vectors, and that helped us then to see the spread within a painting, and then the difference with the cloud of these in another painting. And so we use that for various studies. But this, in a nutshell, says what wavelets do, why they're powerful. They use their information only where needed, and most places it's not needed. Because, of course, even if you took a snapshot of this room, there's lots of stuff going on. But you have zillions of pixels. And most pixels are going to be very similar to their neighbors. You don't need to encode, oh, this, and then this value, and then this value, and so on, by taking these differences over scales. Now, remember, I was averaging every time. Well, let's do it again on something one-dimensional. So if you imagine one line through your picture, things are varying smoothly, and suddenly you might have big edges. Okay, we approximate that by making it pixelized. So imagine you make a very fine scale approximation, constant. Okay, that's your fine scale, that's your pixelized image. You take averages in groups of 2. And you do that again. and again. Now, every time I lost information, as we did before. So from here to there, you see in 3 spots, I've marked you the difference between the original and so on. If I only look at those differences, those are the little things that I need to add to the coarser thing in order to get the finer. And I have that everywhere. So these 3 are really, have a whole lot of siblings with different heights, and that's that difference function. And the same thing happens here and here. So I have these 3 successive families of differences. And together with a very coarse approximation, if I add that back, I get the fine again. That's, I mean, in practice, what you do is you don't just take that minus that. You do it a little bit more smoothly, and so there's nice mathematics that goes into all. But that's not really, that adds beauty technically in mathematics, and you have to work hard in order to make everything work out. But the essence of it is here already. So these are the building blocks that I was using. I have a building block very narrow, wider, wider, and I put them at different places with different amplitudes, clearly. So clearly, I'm writing, if I take that function and I scale it by different scales, then it and its translated versions express these different functions. So that's how wavelets help decompose information into many different scales. And the wavelet is that building block that you stretch to different scales and you put in different places. And this emerged in the 80s and 90s as a synthesis of ideas that came from many, many backgrounds. And in fact, some of it is related to old ideas in mathematics from the 30s. The synthesis, so I'm here, I want to give you an overview from my vantage point. Different vantage points might structure this overview differently, but my vantage point is that in mathematics, in harmonic analysis, which is decomposing things into Fourier modes in sine and cosine waves, it was found out by Littlewood and Paley that it's very useful to group all these different frequencies. So here you have the different oscillations, e to the INX, all these different frequencies, and these signs that you can superpose in order to make arbitrary functions into subgroups, dyadic rings. So what that means is that you have the 0 frequency, and then you take the 2 numbers of the smallest frequency smallest frequencies next to it, and then you take 2 and 3, and now I'm going to take 4, 5, 6, a ring that's 4 times as wide, and so on. And so every time my ring becomes twice as wide. How is that related to what we saw? Well, we were looking at our building blocks, which put the oscillations in a little interval. The next building block was twice as wide. So it put the same oscillations in an interval twice as wide. You had a scaling factor of 2. The next one went twice as wide again, another scaling factor of 2. Here I'm taking frequencies together that belong in the same band of factors of 2. So that's the link. It turned out this was a really interesting thing. So I've rewritten my sum as a sum of saying I'm going to sum over these different colors, frequencies 1, 2, the next band gives me a third band, and so on. And then within each band, I sum. Why is that important? Well, it turns out Fourier transforms, and I'll come back to that at the very end of the talk, are incredibly powerful. They contain a lot of information, because you can always go back. They have all the information. But they're also a little dangerous, meaning if you have things that have some functions that have some singularities in this, continuities, spikes, and so on, then by changing the phase factor of these numbers, which are typically complex numbers, you can really change the nature of that singularity. I mean, for tame singularities, it doesn't matter. But as soon as it's not quite tame, you can all of a sudden, floop, make it much worse by changing the phase. So I'm not touching the absolute value of these things, just the phase. I can even change it by making some of the coefficients a bit smaller and a bit bigger. I mean, which is horrible. I mean, applied mathematician, you believe that it doesn't matter whether you know everything up to the finest decimals. You can round off. Well, forget about it if things are that sensitive. For you, if you can really make singularities worse by rounding off, or by changing the phase. But it turns out that the phase in front of these bands is safe. You don't change the function, of course, but you don't change the nature of the singularity by taking them in groups like that together. And that actually reflects, that was the root of properties that are reflected in wavelets, where wavelet coefficients turn out to be much more stable in that sense than Fourier coefficients, meaning you can shrink them and you're not going to hurt the singularity of your functions. They're going to not change in nature all of a sudden. They don't floop out of the space of things you're interested in. So that's Littlewood-Paley theory. And those roots that have been developed since the 30s and then Calderon-Zygmunt theory in the 60s and so on are behind powerful theorems that from a mathematical point of view are so fantastic about wavelet theories. They explain mathematically why you can do so much with them. Well, approximation theory was also one of the roots. That's pretty clear since we talk about successive approximations. I'm not going to go into that. But in fact, the synthesis that happened in the 80s didn't come from mathematics. They were these mathematicians who knew all these things, but they lived in their own little world, and they didn't really talk to people who had applications. It came from a completely different thing. So, in fact, it came, from my point of view, from seismology. There was a man worked for Alpha Aquitaine in France, who devised an alternative to the short-time Fourier transform. Now, the short-time Fourier transform is something that you can use to analyze the frequency content in functions locally. I mean, when we think frequency, you think a music score. Well, a music score is not a frequency analysis. It's a time frequency analysis. The Fourier analysis of let's say, the Ninth Symphony of Beethoven would be an immense room, completely irrealistic. An immense room, I mean, it's like a three-body science fiction novel kind of. An immense room full of tuning forks with a little mechanism that manages to exactly at the split second hit every tuning fork with exactly the right amount, and they are undamped, and they get hit at the right time, exactly the right amount, and then they all start interfering, all the sound from all these tuning forks, and they play a 1.5 hours symphony together. That's what a Fourier transform does. That's not what you do at a music score. It tells you what note to play when. What that means is you localize in time, and then you say what notes to play. So you localize in time with an envelope, and you fill in frequencies. So this is used a lot in seismography. And Jean Morlet said, but look, if we want high frequencies, we take our envelope, and then we have these high frequencies over the whole thing. If it only happens in a little bit of it, then they have to conspire in the rest of it in order to cancel out, and indeed they need to. And that takes a lot of work for these poor coefficients. So instead, he proposed something where you would have things that had a number of oscillations, and you would make them more narrow and more wide. And he learned to work with that and use them. And his colleagues didn't believe him. They said, you're proposing a new mathematical transform. If it was true, it would be in the books, and it's not in the books. So, of course, it was not in their books. It was in completely different books. But so he met, through a common friend, Alex Grossman, who worked in quantum mechanics, and he recognized constructions from quasi-classical expansions in quantum mechanics, and that was the first, and that's actually where the name ondelet wavelets was coined, because they existed in seismology, but they talked about the wavelet of such and such, depending on who had proposed the envelope, and then the such and such dropped because it was no longer necessary. And so that's you have mathematics, seismology, and quantum physics joining in to give us, actually the first wavelet basis was constructed in 1985. Now, computer vision, I've talked to you about images and looking them, making them, blurring them more and more and comparing those. That was something that was done a lot in computer vision in that time. And Stéphane Mallat was the person who linked that with this multi-scale analysis, multi-resolution analysis in computer vision. And then, after all that happened, people wanted to apply this to signal analysis. And if you had to do that, all the bases that had been constructed that were nice and smooth had infinite support. And so you had to truncate. And then came in a reflex of pure mathematicians who said, you have to truncate. Okay, so you lose some of the mathematical beauty. Okay, it always happens. And I never agreed with that. I mean, that's another of my hobby horses. I don't believe that. What you should do is use all the math that you understood and say, I want it to be applicable. It might be, and it does happen, that you then show the two are not compatible, and then you optimize for doing the best equilibrium. But in this case, that was not the case. In this case, you could have it completely practical, finite support, and all the beautiful math, and that's what then led to... So that then gave rise to new constructions that are used in a lot of applications. So you see, you had this whole synthesis of things, ideas coming from so many places, and it led to so much more. I mean, it led to many, many applications. And the conferences that happened then were very exciting because people were talking together and so on, who normally would not have met. And I hope it showed to all the people who came from harmonic analysis that it's so useful to talk, not just within your field, but also to lots of people outside your field, to blow your information. There is an emblem of a French dictionary called Larousse, who does dictionaries anymore, but I mean, which is, it shows a dandelion with the wind, and the thing is, je sème à tout vent. In every wind do I spread stuff. And I think that's how I view mathematics. And it leads to many applications, but communication is so important in mathematics, as it is in many fields. But I mean, mathematics and its link to the whole science operation is so important. So, yes, so back to all these things I've worked on. I can tell you different stories about each of these, but I don't have time, so I won't. But I'd like to finish this little intro to a day that it will be really exciting and where we'll learn much more than these pet peeves I hold. A question I get asked sometimes is, now that AI, deep neural nets, can do so much more, doesn't that mean mathematics is of the past, is superseded, we'll no longer need it? And my answer is an emphatic no. Not just because I'm a mathematician and I want my students to still have jobs, but I believe that with respect to these fantastic applications, we are where mathematicians were at the start of the 19th century with respect to Fourier analysis. I mean, when Fourier proposed his Fourier transform, by the lights of the mathematics of his time, this made no sense. He was decomposing in order to solve the heat equation, where you might have discontinuous initial functions, into smooth things, sines and cosines, and using that in order to then construct the solutions at later time. It didn't make sense to decompose things like that. But he did, and it worked. And of course, tons of people started using it, as they should. As we should use neural nets. They work, they do things we couldn't do, and of course you should use that. But on the other hand, we don't really understand what they do. I mean, using these zillions of parameters, and then it goes against what we understand, what we thought we knew, and so on. Doesn't mean we shouldn't do it. Of course we should do it, and we should learn how to work with it. But we should also learn to really understand what's going on. Because once we understand what's going on, we understand what lends it that power, we'll be able to do so much more. I mean, everybody will agree with me that we do so much more with Fourier analysis now, or even at the end of the 19th century than we did at the beginning. But so it's a big challenge for mathematicians. We have our work cut out for us, and let's do it. Let's learn this 2 days, all the things that have stuff, questions, important challenges on which we can work and will. Thank you.